is the first video about trigonometry, which is the sort of mathematics of triangles. But I would like to start instead with a graph of a line. So I'm going to sketch y equals 2/3 of x. And if you want a y-intercept, we'll put the +0 in there so you can see it. So that line there starts at 0, and for every step in x, it goes up 2/3 of a block. Or, which will be easier to count, you need to go up 2 blocks for every 3 that you travel over. So up 2 over 3, up 2, 3, up 2, 3, up 2, 3, etc., etc., etc. Be a nice line like this. So on and so forth. So that line has two features. It has a y-intercept at 0, and then it has this thing here, which we've always called slope. Then it measures how steep that line is. Okay, so I'm going to drop some horizontal lines here, or vertical lines here from each of those dots. I'm going to drop one, say, here. And if I do that, you're going to see a 90-degree triangle there, or a right-angled triangle. If I were to measure the height of this triangle, it's just the height of this dot. So that's 1, 2, 3, that's 4 squares. And the distance this way, 1, 2, 3, 4, 5, would be 6 squares. And so if you took the length of this side, 4, and you divided it by the length of that side, 6, you end up with 2/3, which is the slope of that particular line. And that shouldn't be a surprise, because for every 3 steps you take this way, you must add another 2 in order to stay on this line. So any triangle you build on this line should have sides locked in that same ratio. So I'm just going to pick a random dot. How about this one here? Drop a vertical. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 high. And 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15 long. So again, 10 high, 15 long. That ends up giving me exactly the same ratio. So the slope of this line has locked the lengths of the sides of these triangles I'm constructing in the same ratio, right? The slope is the ratio of the sides, because you can't make this one longer without this one getting taller if you're trying to connect to this blue line. So what does that have to do with triangles? Well, in this corner here, there's an angle. I'm going to use a Greek letter alpha for that angle there. Now we've got 2/3 here as the ratio between the sides. I would like some way to connect the size of that angle in degrees to this ratio so that I can think about triangles that aren't necessarily flat. So if I were to draw a triangle like this, it's hard to think about the slopes of the lines on this because it's all off grid. So I need a tool that can connect the slope of this line to the angle that's showing up there. And the thing is this tool called the tangent ratio. So we write tan, T-A-N, which is just short for tangent. And the angle that I'm trying to solve goes sort of in the operator there. So by definition, the rise over run of this particular triangle calculates this ratio here. So I'm just going to write that in there. That is the rise over the run. And if I wanted to figure out what that angle is, I just need to use some algebra to break this function off of my alpha, get it over to the other side. So if you look on your calculator, I don't know if you'll be able to see, but there is a tan button right there. And directly above it is something that looks like this. Tan with a -1 on it. That thing is called arctan. And it's the anti-function to the tangent ratio. The same way that square rooting is the anti-function to squaring, and that division is the anti-function for multiplication. So if I'm trying to do some algebra and I need to get alpha away from there, I just have to apply arctan to both sides. I'm going to apply arctan to tan. And I'm going to apply arctan 2/3. Now on the left side, the tan and an arctan undo each other. So the only thing that's left is alpha, my angle. On the other side, I just have to type that into my calculator. So 2/3, and then arctan. So I'm going to have to hit second function, and then tan. And I end up with 33.69. So a line with a slope of 2/3, up 2/3, makes an angle with the x-axis of exactly 33.69 degrees. And so now you're able to connect the ratio of two sides to the angle that makes them, right? Like the size of this angle here is what determined how big this has to be based on how far away from the origin you go. So if I can do that with a graph, I should be able to do this with a triangle. So I'm just going to draw one up here. We're going to try and connect. All right, so suppose I was after this angle here, and I knew that that side was 5 and this side was 8. So I'm going to set up my tan ratio here. Tan of alpha equals. When I set this one up, tan was the rise over the run. Now, rise and run aren't going to work for this particular triangle because it's not oriented like this line was. So I'm going to need some different words for rise and run. First off, I'm going to look at the rise, this side over here. This was the rise. Do you notice that the angle was on the left side and this is on the right side? So those are opposites, right? This is the side opposite from alpha. So instead of having rise in my fraction, I'm going to instead phrase it as the opposite side. So why would I do that? Well, in this triangle here, I can't tell which of these numbers is the rise and which one is the run, but I can see that the 5 is directly opposite the triangle from alpha. So the angle I'm trying to find with, its opposite side is way over there. It's the side that isn't used to make the angle. Right? You needed this side and this side to make alpha. The third side is the opposite one. So in this particular example, my opposite side would be 5. Now I need a word for the run. So that's over here, from here to here. The word that we end up using for that is called the adjacent. And that's a fancy word for beside. I'm going to toss that in here, adjacent. So again, run was fine for a triangle oriented like this because I could see rise and run from the graphing point of view. But in one like this, the adjacent side is going to be over here. It's one piece of the lines that actually make that angle. Let me just label that on there, opposite, adjacent. So in this particular example, the value there is 8. And this one is often difficult to identify because there are 2 sides that make that angle. And the way you tell them apart is that this side here, this already has a special name. That's the side that is directly opposite from the 90-degree corner, which makes it the hypotenuse of the triangle. So when you're trying to figure out which side is which, the hypotenuse is always the longest side. It's always the one across from the 90-degree corner. The opposite will be the one that is not touching the angle you're working with, and the adjacent is the one that's left over. I think that's the easiest way to think about it. So having built that, this opposite over adjacent, out of the idea of rise over run, I'm left with tan alpha is 5/8. So if I want to find alpha, I just have to apply arctan to both sides. And if I put in arctan 5 divided by 8, I get 32 degrees. So the angle in this corner, if that's 90 degrees, that's 5, and that's 8, this angle must be 32 degrees. So you've got a tool now to be able to take the lengths of sides and convert them into the angle that makes them happen. So I'm going to clear this off. We'll do a couple more examples of finding angles, and then we'll do a couple examples of finding sides. Okay, so I got 2 right angle triangles there, and I just labeled some sides. Note that they are not to scale. They're just sort of rough drawings of triangles. Now I'm going to try and find this angle first. So you set that up by remembering that the tan ratio for an angle is the opposite side over the adjacent side. So I'm going to look across the triangle from the angle I'm trying to solve for, and I see this. That means that 6 is the opposite side. So in it goes. I'm going to find the 90-degree corner and look across the triangle. And I'm going to label that as the hypotenuse, which means the side that remains, this one here, that must be the adjacent. And it goes. So I have tan of alpha equaling 6 divided by 4 is 1.5. So to finish that, I throw arctan to the other side. And I just need my calculator to get an answer. I'm with 56.31 degrees if you round. Now you'll notice that this triangle has another angle up there, which I'm just going to label as beta. If I'm going to try and find the size of that angle, I need to start by writing my tan ratio. Tan of beta would be the opposite side over the adjacent side. So I'm going to put my pen on the beta angle here, and I'm going to look across the triangle to the side that's not touching it. And I'm going to see a 4 there. So from this angle, the 4 is the opposite side. So I'm going to put it in there. And then I'm going to go and I'm going to look at the 90-degree corner, and I'm going to find where the hypotenuse is. It's still on that side. It won't change. And then the other side that's used to make angle beta, right, this one here, that is going to be serving as the adjacent side. So when you're solving for beta, the adjacent side is 6. Now you'll notice that the 6 and the 4 have just swapped roles when I tried to find the other angle. So when you're finding alpha, 6 was opposite and 4 was adjacent. When you're finding beta, 4 is opposite and 6 is adjacent. They just flip-flop. So to finish here, I'm going to throw arctan on the other side. And I end up with arctan 4 divided by 6 gives me 33.69 degrees, which that's familiar from the previous example. Okay, now if this all checks out, all 3 angles in a triangle added together are supposed to add up to 180 degrees. So I've got a 90-degree corner there, and allegedly a 56.31 degree corner there, and allegedly a 33.69 degree corner there. 0.31 and 0.69 add up to 100. So I've got an extra 1, carry the 1, 3 and 1 would be 4, and 6 would be 10. Carry the 1, 3 and 1 would be 4, and 5 is 90. These two pieces added up perfectly to 90 degrees, which gives me a total of 180 degrees in that triangle. So it all worked out. All right, so another example there. Put alpha down here, I'm going to put beta up there. Maybe to save myself some grief, I'm going to find where the hypotenuse is first. That's there. So if I go to solve for alpha first, tan alpha should be the opposite over the adjacent. So I'm going to go to alpha, look across the triangle. There's my opposite side. That's opposite to alpha. So in it goes, 8. That means that this side is adjacent to alpha. So in it goes. So I have tan alpha equals 8 over 7. Throw my arctan over. And I get arctan of 8 divided by 7. 48.81 degrees. And if I'm going to solve for beta, I set up my tan ratio. Go to beta, look across the triangle, find that side. That's going to be opposite to beta. So I have 7 as my opposite, which means the other side that's not the hypotenuse must be the adjacent. There's an 8 there. So tan beta is 7/8. Beta will be the arctan of 7 divided by 8. Put that in a calculator. Arctan of 7 divided by 8 would be 41.19. And if I've done it correctly, this angle plus this angle will add up to 90. The 40 is 80. 8 and 1 is another 9. So I'm at 89 so far. 0.81 and 0.19 is an extra 1, bumping me up to 90 degrees. So I know I've done that correctly. So I'm going to clean this off, and we're going to try and find some side lengths using tan, and then I think you're good for the practice problem. In this particular triangle, I know one of the side lengths, and I know what angle the hypotenuse and this side make to one another, but I don't know how long that side is. So I can still do this with a tan ratio. So I'm going to start with that. Tan alpha is the opposite side over the adjacent side. Now I have to figure out which side is which in this triangle. So I'm going to find my hypotenuse, start at the 90 degrees and look across at it. There's my hypotenuse here. And then I look at the 50-degree angle and I look across the triangle and I see this question mark. So the unknown side is the opposite of the angle here. That means that this thing has to end up being the adjacent. So I'm going to start filling some stuff in. Oh, I should label that opposite. This time, instead of having to solve for the angle, I know that it's 50 degrees. The opposite side is some unknown that I don't have, and the adjacent side is 12. All right, so I'm going to type this into a calculator, tan 50. And I get 1.191753593. Now you can round that wherever you'd like to, depending on how many decimals of accuracy you want. Usually I keep 3, so I might have rounded that to 1.192, but I'll just leave the whole number up there for now. So that equals some number divided by 12. Well, this is just a basic algebra statement now. I want the question mark by itself, so I need to get rid of this division by 12. And you undo division by multiplying. I'm going to multiply both sides by 12 here. And that horrendous number multiplied by 12 gives me 14.301 if I round it to 3 digits. So the only way for this angle to be 50 and that side to be 12 is if that side is 14.301 units long. So you were able to initially take a line that you knew the height and the run of and use that to calculate the size of the angle. But if you can do it that way, you must be able to do it backwards. So running it backwards allows you to take a side length and an angle to find a second side in a triangle. So I'm going to just quick draw another example here. I'm going to say that we know that this is a 42 degree here, and that that side is 11, and I don't know that side. Okay. So we're talking about tans here. So tan ratio of an angle is its opposite over the adjacent. I'm going to look at this 90-degree corner, and that's going to tell me where my hypotenuse is. I'm going to go from the angle I know, and that will tell me what side is the opposite. And the other side remaining must be the adjacent. Okay, so start filling it in. Tan of 42 degrees must be the length of the opposite, which is 11, over this unknown side. Okay, that's a little awkward. It's got the variable in the denominator, and we're going to have to do a little bit of manipulation in order to make that work. Or you could remember from the other examples, right, the angle ones, that if I did the tan ratio of this other corner here, the roles of the opposite and adjacent would switch. So your variable would pop up into the top like this one did, and it would be a little easier to do the algebra. I will eventually finish this one so you can see it. But for now, let's try using the other angle. If I look over here, how big does that have to be? Well, there are 180 degrees in a triangle. I've got a 90-degree corner, and I have a 42-degree corner. That leaves me with 48 degrees. So this has to be 48 here. So if I set that tan ratio up, call that beta. If I use 48 degrees, the opposite side from 48 is the question mark, and the adjacent side to 48 is the 11. So I have this set up with the variable up in the numerator, which is a touch easier to manage from the algebra point of view. So I'm going to type in tan 48. I'm going to get 1.111 if I round it. There are a lot of ones in this example. I need the question mark by itself, so I need to undo this multiply by 11, or divide by 11, so I multiply by 11. And 1.111 multiplied by 11 gives me 12.217. So, if you work smart, not hard, and you pick the angle so that the unknown is across from it, then you can just crank out the answer like that. If you want to do it this way, you're going to have to get tan 42 as a number. Tan 42 gives me 0.900 if I round it to 3 decimals. Now, I'm going to have to break this division here by multiplying by the unknown. So I end up with 0.900 question mark is 11. And I need to break this multiplication with division. So I'm going to have to divide both sides by 0.9. And I end up with 11 over 0.9, which is 12.217 if I round. Which of course it has to be because both of these methods have to return the same side length. So it's really up to you. If you can handle this, move the question mark, then move the number. If your brain can tolerate that, then just do it this way. If you find that a touch mysterious, then you are always free to use the other angle, which will end up changing the order of those pieces in the fraction, and you can get the variable up on top where it's a little easier to handle. Okay, so that's the tangent ratio. I think you're ready for the practice problems.